When collecting a simple random sample that will be used to estimate a population mean, how many sample values must be obtained? For example, suppose we want to estimate the mean IQ of NASA scientists. The Wechsler IQ test is designed so the mean is 100 and the standard deviation is 15 for the population of normal adults. So say we want to be 95% confident that our sample mean is within 5 IQ points from the true mean. Determining the sample size of a simple random sample is a very important issue because samples that are needlessly large waste time and money, and samples that are too small may lead to poor results. So if we use the expression for margin of error, and let's recall what that is. Margin of error is equal to the critical value times sigma over the square root of n. This is the margin of error when sigma is known, for the mean when sigma is known. And if we solve this for n, we rearrange this equation and get n equals, we'll end up with n equals this entire quantity squared. The critical value times sigma all over e, that whole quantity squared. Note that the sample size, capital N of the population, that capital N that represents the population size, that doesn't have any bearing on what size our sample should be. We don't have any place here for including the population size, capital N. So that's a good thing to note, that it has nothing to do with the size of our population. Okay, so our rounding rule when calculating n is the same as we found when we were working with the proportion. To have the confidence level we want, we will always round up to the nearest whole number. It doesn't matter even if we get 100.002, we'll round that up to 101. Okay, let's look at an example. Say our example that we're working was a 95% confidence, right? It said 95. So that tells us z alpha over 2 is z.025, and we know from experience now that's 1.96. They told us our standard deviation for IQ scores is 15, and that we want our margin of error to be within 5 points, 5 IQ points. This isn't a percentage like proportion. This is, when we're talking about the mean, it'll be in the units of measure, whatever we're measuring, whether it's pounds or IQ points. That's how we'll interpret that. So 5 IQ points. Okay, let's plug in what we know then. So n is equal to 1.96 times 15 over 5, this entire quantity squared. So we get 5.88 squared, which is 34.57, and we would then say that 35 NASA scientists should be included in the sample. That's what our sample should be. And based on this, we don't need more than that, but we can't use less than that either. Okay, so we've been talking about in this section all about sigma being known, population standard deviation. In reality, sigma is not usually known. That's a pretty unusual situation, but it gives us a start for understanding confidence intervals for the mean. And in the next section we'll talk about constructing confidence interval estimates of the population mean where sigma is not known, a much more common situation. And when we talk about finding the sample size, of course our calculation involves sigma. Sigma must be known, but what if it isn't, which is much more common? If sigma is unknown, we can estimate sigma using the range rule of thumb. Haven't seen this in a while. You might recall that at one time we saw sigma was equal to approximately, I think we were told approximately equal to the range divided by 4. So if you have your data and you can calculate the maximum value, remember what that is, maximum value minus the minimum value, and divide that by 4, then that's a reasonable estimate for the standard deviation. And then you could then go calculate n using that value for sigma. Or you could just take a quick sample, calculate the sample standard deviation, and use that as an estimate for sigma. Or you can use the results from a previous study.